This is a relatively straightforward phase diagram example and phase diagram question. And so again, the point stands that if you feel like this is really confusing or inaccessible, just treat these figures like a graph and just read them like you would read any other graph with the x-axis and the y-axis. And that's all we have to do with this question. So what phase do we expect water to be in at 0 degrees Celsius and 4.58 torr? So if we look at our graph, we do have our temperature given here on the x-axis in degrees Celsius, but on the y-axis, our pressure is given in kPa. So we do have to do a little unit conversion, converting that 4.58 torr to kPa, so we can actually compare it with the graph. And so from your unit conversion sheet, you should have that 1 atm 760 torr, and that 1 atm is also 101.3 kilopascal or kPa. And so I'm going to go to kPa in this case because that's what my pressure unit is here, right? If the pressure units matched in the question and on your phase diagram, you wouldn't have to do this step, but I thought it would be fun to do a little bit of a unit conversion. So we do 4.58 divided by 760 times 101.3. And we've got 3 sig figs there, so we'll take 3 sig figs here. That's going to be 0.610 kilopascal. Okay, so that's the pressure that we're working at now, 0.6 kilopascal and 0 degrees Celsius. And so now we just need to go to the graph and find that. So here's 0 degrees Celsius. 0.61 is going to be really, really close to 0.6, especially based on this scale here. And we can see that those lines intersect somewhere in there, right? There's a little bit of margin for error, but in either case, water would be a solid. So another type of phase diagram question that we might have to work through is looking at the different phase changes a substance will experience as we heat it up under certain conditions, or as we add heat to it under certain conditions, or maybe take heat away from it under certain conditions. So in this case, we're going to have water, and we have the phase diagram of water here. That water is going to start at negative 20 degrees Celsius and 2.15 torr, and we're going to heat it to 50 degrees Celsius while keeping that pressure constant. And so we want to know what phase changes are going to occur. So the first thing that we should notice here is we have a pressure here, 2.15 torr, and our pressure on our phase diagram is in kilopascal. So we do need to bring those two things into alignment. We need to do a unit conversion, and it's much easier just to convert that 2.15 to kilopascal versus trying to read the graph and convert those numbers to torr. So that's what we're going to do. So we're going to take 2.15 torr and convert to kilopascal. Maybe that's not the best place to put that. Let's go down here. 2.15 torr times, we'll go to ATM first. So 1 ATM, 760 torr. And then we can go from ATM to kilopascal pretty easily. And I'm using conversion factors that are going to be on your conversion sheet. Or at least I'm trying to do that from memory. I don't have a copy of that right in front of me. So 2.15 divided by 760 times 101.3. That lets us know our starting pressure is 0.286 kilopascal. So pretty low pressure here. Okay, let's see if we can mark that on the graph. And we got to do some estimation. You can see the scale on the y-axis here is pretty nuts, right? It goes up pretty quickly. So 0.3 kilopascal. We're just going to mark it sort of down here. We know where 0.6 is because the triple point is marked there. I'm going to say 0.3. We'll say somewhere in there, right? It doesn't have to be exact. Negative 20 degrees Celsius, I'd say that's fair to say that that's down here as well, right? So we're probably starting with solid water. Can we call it ice? Let's call it ice. Okay, so that's initially. Let's see where it's going to go. So we're going to keep that pressure constant, and we're going to bring it up to 50 degrees Celsius. And so 50 degrees Celsius, the x-axis is a little bit better, so we can sort of assume that we're about halfway to boiling there, or halfway to the normal boiling point there. 100 degrees Celsius. So this is now going to be water vapor, which is of course a gas. Okay, and if we draw a horizontal line from that initial pressure of 0.286, so constant pressure, we heat it up, we go from solid to gas. That's only one phase change that happens there. And that's a real fun phase change. Anytime we go directly from solid to gas without passing through liquid, we call that sublimation. And so that is the phase change that will occur if we take water from negative 20 degrees Celsius to 50 degrees Celsius under constant pressure of 0.286 kilopascal. There's several types of questions that might come out from being asked about a heating curve, but I wanted to present a quantitative example to sort of work through here real quickly. So for substance X, we want to calculate the heat in joules added to 20 grams of that substance if we're in segment 3 of this heating curve. And so segment 3 here is a sloped segment. So that means that when we calculate the heat, or Q, it's going to be MC delta T in that segment, right? So the flat segments, the heat is equal to the enthalpy of the phase change, and in the slope segments, the heat is equal to MC delta T. Okay, so we're going to solve for Q. M is the mass of the substance, that's 20 grams. C is the specific heat of the substance, and as you saw with the heats of phase change lesson, the phase that the substance is in, the specific heat of the substance depends on the phase that it's in. That's a better way to phrase that. So in this case, we are given two specific heats. We're given the specific heat of the solid substance X and the liquid substance X. And so we have to figure out which one to use here. Well, if we just kind of think about this logically, I think we can figure out which specific heat to use. So in segment 1 here, what we're doing is we're heating up a solid substance, right? It's at low temperature. So we add heat to that substance. Segment 2 represents when the substance is melting, right? So that's going from a solid to a liquid. And so that means in segment 3, we're heating up the liquid, right? This is vaporization. This is the liquid boiling. And then here we have heating up a gas, right? So for these heating curves, you'll notice that the first non-sloped segment is melting, and the second non-sloped segment is boiling. So that means that in this region here, region 3, we're dealing with a liquid. So we're going to use that specific heat, so that's 5 joules per gram degrees Celsius. And then lastly, we have to get our delta T, which is going to be T final minus T initial. And if we look at the graph, not look at the glass, look at the graph, our final temperature for this segment is about 55, and our initial temperature of the segment is about 5. So that delta T is going to be 50 if my math is correct. Okay, and then we're just plugging in the calculator, doing 20 times 5 times 55 minus 5, which is 50, and we come out with 5,000. We're going to report this to 2 significant figures. I think would be the best option, and to make that really easy for us, we'll put it in scientific notation. 5.0 times 10 to the third joules of heat added to that substance. Okay, let's look at a little bit more of an involved example where we're going to need to use a heating curve in order to answer this question. So in this case, we have 50 grams of water that's at negative 10 degrees Celsius. That's ice, right? And we're going to add 1.6 kilojoules of heat to that water. And we want to know what the final temperature is going to be. So this is not as simple as, or not necessarily as simple as a Q equals MC delta T calculation. And we're actually not even given a heating curve here. So I'm just going to sketch one to show you that you don't need a really detailed graph in order to use that heating curve as a tool. You just need to have sort of a general idea of what's happening. So let's sketch a heating curve here real quick. A heating curve for water. Let's do better than that. Okay. Now I know for this heating curve, in this case, it's going to start at negative 10 because that's the initial temperature that I'm given here. And it's going to heat up and undergo a phase change. And since we're dealing with water, I know what temperature that is. It's 0. And then it'll heat up again and undergo another phase change. So this is now liquid water that's undergoing another phase change. I know that this temperature up here has to be 100. And then once we get water vapor, we can heat it up some more. So it's going to look something like that. Okay, so this is temperature on the left axis and then just heat added or time on the y-axis. And my graph extends beyond my axes, but that's all right. I think we get the point. Here's the tricky part about this problem. If 1.6 kilojoules is enough energy to get us to the melting point temperature and through this phase change, we have to take that into account of our calculation, right? Because remember from our other slides, anywhere sloped, we can calculate the heat by doing Q equals MC delta T. And anywhere flat, the heat is equal to, Q is equal to N, the number of moles, times the enthalpy of the phase change. So that's the heat of fusion here, because it's melting, and the heat of vaporization here, because it's boiling. And so we have to take that into account as we're doing this calculation. So the first thing that I'm going to do is I'm going to calculate how much heat is needed to get us to our melting point temperature of 0 degrees. So I'm sort of doing like a theoretical calculation here. Okay, I've highlighted that segment in blue, and I'm going to do this calculation in blue. So the heat there needed to get us up that segment for 50 grams of water. Now, water in this segment, right, we're below the melting point temperature, so this is solid water. So that means I need to use the specific heat for the solid water, just 2.06. I'm going to leave the units off to save a little bit of space. And then the delta T is going to be T final which is 0, right? That would be the final temperature if we heat it up here. So 0 minus the initial temperature, which is -10. That's prescribed in the problem. So 0 minus -10 is a +10. That's our delta T. Okay, and if I've done my calculation correctly here, that's 1,030 joules. So that means it takes 1,030 joules to heat water from -10 degrees Celsius, which is the temperature that we're at now, to the melting point temperature. Do we have more than 1,030 joules? Yes. We have 1,600 joules, right? 1.6 kilojoules. So that means that we are beyond this segment. Okay, so our final temperature is greater than 0. We have melted that water completely. Okay, so let's do another sort of theoretical calculation. We'll do this one in red. So we're going to go to the next segment. So let's calculate the heat for that red segment, right? And remember that heat there is going to be the number of moles of water times the enthalpy of fusion. And it's fusion because this is melting here, right? Vaporization, boiling is up here. This is melting, so fusion. Our number of moles of water is the 50 grams divided by the molar mass. It's like 18.02 grams per mole. And the enthalpy of fusion, given over here on the left side, is 6.02 kilojoules per mole. Okay, so the heat here so 50 divided by 18.02 times 6.02. It's 16, we'll do 3 sig figs, 16.7. And this is in kilojoules because I had my enthalpy of fusion was in kilojoules there. So the heat needed for 50 grams of water to completely undergo that phase change is 16.7 kilojoules. So in this case, that is more than what we were given, right? And so the story here is we had 1,600 kilojoules initially. We used 1,030 of that to get it to a temperature 0 degrees Celsius. And so that means we have 570 kilojoules left. And that 570 kilojoules is adding heat to that water, melting it. And so we're somewhere in this flat region here, in this red region. We don't have enough heat to completely go through that region and start increasing the temperature again. We're somewhere in that horizontal region. And so the convenient thing there is we notice that for those regions, the temperature doesn't change, right? This is a no-sloped part of the graph. And so therefore, the final temperature must be 0 degrees Celsius. That water is in the process of undergoing the phase change. We don't have quite enough energy to completely change its phase.